Hello everyone, my name is Wen-Chin Huang from Nagoya University in Japan. Today I'm going to present LDNet, Unified Listener Dependent Modeling in MOS Prediction for Synthetic Speech. This is a joint research project with National Institute of Informatics, Japan. We're interested in the task of speech quality assessment. This is important to evaluate speech synthesis systems like text-to-speech, TTS, and voice conversion, VC. The gold standard has been to ask human to listen to each of these samples and rate the samples to give them a score. So usually we will use this thing called mean opinion score, MOS, because we try to collect scores from multiple people and average over them to get the average rating. The downside of this kind of method is that it's very costly in terms of money and time. So instead, people have been focusing on objective measures. So for example, in recent years, thanks to the development of deep learning, this kind of method has been greatly improved. But we still need to improve several things. So for example, it is very hard to get a lot of training data for the deep learning models to be trained. And second, there still exists a performance gap between the predicted scores and the true human ratings. So before we jump into what are the core of this research, let's introduce some basic settings. So given a data set, we will have n speech samples in it. And for each sample, we will have n listeners that listen to each of these samples and try to give a score. So let's say we have like 5 people. We will have 5 people to listen to this sample and give 5 scores. So we can denote the mean score of these 5 scores as S bar. So there may be a total of 100 listeners, but we only have 5 listeners to listen to each of these samples. So each listener does not have to listen to many samples. One representative method is MOSNet, where we train a model, the MOSNet model, to regress to the mean score by using a MSE loss. So during inference, we just use this MOSNet to just predict the score. For evaluation, we report system level and utterance level scores using 4 metrics: the MSE, the LCC, which measures the linear trend, SRCC, Spearsman correlation, which measures the ranking, and K-tau, Kendall-tau correlation, which also emphasizes on the ranking. The dataset, which is the most commonly used one, is the Voice Conversion Challenge 2018. It has around 20K samples in total, and we have 4 listeners listening to each sample. It is usually split such that there are around 13K samples in the training set. Now, for this research, we curated another data set called BVCC because we merged samples from scientific challenges, including the Blizzard Challenge, which focuses on TTC, founded in 2005, and VCC, which focuses on VC, founded in 2016. We evaluated all these samples using a very large-scale crowdsourcing listening test, so that in total, we collected 7K samples, and each of them has 8 listeners. But the training set actually just contains 5K samples, which is just too small to train a MOSNet. As we can see here, on VCC 18, MOSNet can get LCC and SRCC around 0.9, but on BVCC, we only have like 0.2. So 5K samples is just too small. So one way to increase data is to use listener-dependent scores, LD scores. So for VCC 18, we have 4 listeners, so it will be 4 times larger. And for BVCC, it will be 8 times larger, which is good. So there's this one paper called MBNet that extends the idea of MOSNet, so that what it does is it first uses the AMINet to predict the mean score, and then it tries to define a bias net to predict the bias score. The bias score is defined to be the difference between LD score and the mean score. So the bias net is conditioned on the listener data, listener ID, so that during inference, only the mean net is used because we assume that there's no listener during the inference. Okay, so the architecture is just looks like this. It's just a bunch of convolutional layers and recurrent layers. Now the efficiency of MBNet is that both MinNet and BiasNet take the speech as input. We know that only the MinNet is used during inference, so the BiasNet is only used during training. So it acts more like a regularization. But the BiasNet also takes speech as input, right? So we know that speech is has a lot of variation in it, so we need a big model to train the bias net. But we think that there should be some shared common behaviors. So, for example, listener independent features between the bias net and the mean net should be there should be some parts of these models that can be shared. So in light of this, we designed the listener dependent net, LDNet. So the LDNet is trained only on the LD score. Okay, so we have the input speech and it goes into the encoder. The encoder will be responsible for learning listener independent features. And then the decoder will be conditioned on the listener ID to finally generate the LD score. So we may ask that, so MBNet uses MinNet as inference. So how about LDNet? We actually propose all listeners inference, which means that during inference time, we will simulate the decisions of each training listener, and then we average over them. So for example, we have 100 listeners, right? So we will simulate the scores from all these 100 listeners and just average over these 100 scores. So as you can see, this kind of method is very general because it can be applied to not only LDNet, but also MBNet, because MBNet can also use a listener ID to generate the 100 LD scores and just average over them. So this is a very general idea that is in contrast with MinNet inference. Okay, so this is all listeners inference. This is the basic idea. And for the model architecture, we think that first, the decoder should be made simple because our assumption is actually from the MBNet paper is that listener preference only adds maybe, for example, a shift. So some people are very strict about samples, so they tend to give lower scores. So we will give a negative shift, and some people will give positive shifts. So it should be very, very simple. It should be just like giving very small shifts. So in our research, we only designed a very simple linear layer and an optional RNN layer. So that is just very simple. The encoder, on the other hand, should be strong because it should be able to handle the high variation in speech because it takes raw speech as input. Okay, so this is the reflection on model architecture. We still have the mean scores, right? So we should be able to use them we should be able to utilize them. So the first way to utilize the mean score is through MinNet. Okay, so this is the original LDNet. But of course, we can condition a MinNet on the encoder output because the encoder is responsible for listener-dependent features. So the MinNet should also be conditioned on listener-independent features. So yeah, we can use the mean score as a very natural regularization for the encoder. So this model is called LDNet MN. The second way to utilize the mean score is mean listener. So recall that all listeners inference need multiple forward passes because we need, for example, 100 forward passes to get all the scores from each listener. This is very costly. So instead, we propose to learn a virtual mean listener by extending the training set. So for each sample, originally we have n LD scores from 1 to m, but now we add another score, which is simply just the average of all the m scores, and then we denote it as S bar. And the listener ID of this corresponding S bar comes from a virtual mean listener. The good thing about this is that in addition to all listeners inference, which needs to run n forward passes, we now can use the mean listener inference, which requires to only run one forward pass, so that things will be very easy. We just need one forward pass. So it will be very effective and it will be very efficient. Okay, so these are the two ways to utilize the mean scores. So for the models, for the competing baselines, we just compare with MOSNet and MBNet. And for LDNet, we compared 3 kinds of encoded variants. MBNet style CN is very huge, and MobileNet V2, which is designed for mobile devices, so it's smaller, and MobileNet V3 is even smaller, but more efficient. For decoder, we designed a very, very simple feed-forward network, FFN, but we also optionally considered a recurrent neural network-based, RNN-based decoder. So we have 5 observations in total. The first observation is that if we compare MBNet using MinNet inference and all listeners inference, we observe that the MSE is greatly reduced. This is because that if we average over 100 listener simulated results, they will be more stable. Okay, so the MSE will be smaller, but not so different in terms of correlation coefficient. But still, all listeners inference is better than mean-end inference. Number two, we compare the encoder variance, and 1/3v3 is among all of them achieves a balance between model size and performance. As you can see that performance is actually the best, and it kind of reaches a balance between the model size and performance. The third observation is that we don't actually need a decoder as complicated as RNN. We actually need just the EFFN. It's very simple. It's just a linear layer. So you see the model size is just so small, but the performance is almost the same. And on some metrics, they are even better, for example, MSE. The fourth observation is that the ambient MN, which uses the MinNet, is not so effective because the numbers are not improved. But on the other hand, LDNet ML is actually much better. As you can see in the last row, that it reaches, many of them reaches the best performance. But sometimes all listeners inference get better scores, and sometimes ML listeners will try to get better scores. So for conclusions, we integrated recent advances in LD modeling for MOS prediction. We propose LDNet, which has a more advanced model structure and several inference options for efficient prediction. We justified the model designs, and we show that LDNet ML is actually the best way to utilize the mean scores. And it is actually effective, more effective on DBCC, and not so much in VC18 because DBCC has 8 ratings per sample, and VC18 only has 4. So since it is a method that tries to model the listener-dependent behaviors, so this is what we expect. So finally, we would like to mention a follow-up. So we held the Voice MOS Challenge 2022. This is a scientific challenge that just launched this year, and it was selected as the special session at Interspeech 2022. It was hosted on Coda Lab, which is some kind of more scientific-oriented version of Kaggle. We have 2 tracks. The main track uses the DBCC dataset, and the other domain track uses a hidden, but it's actually a hidden ear from the Blizzard challenge. Okay. LDNet was used as one of the baselines, and we also have 2 other baselines where you can find them on the challenge page. So the datasets and the baselines links can all be found on the Coda challenge page by scanning this QR code. And we also have the challenge summary paper also on the archive, so you can read it. Finally, we welcome you to come to our special session at this year's Interspeech so that you can hear our summary and you can hear how other top systems, how they do their modeling in this task. Yeah, that's all. So thank you for listening. And if you're interested, please come to see our poster session.